7.1 in this video. As you can see on the screen, these are the main topics that we will be talking about in this section. We will begin with a description of what complementary angles are, and then from there we will move to trigonometric relationships between complementary angles. It's a very neat set of formulas that we will look at. Number 3, we will look at the squared identities. You've seen these before, but we're going to look at them and use them in more detail in this section. But you've seen the squared identities before. And finally, number 4, we will use these relationships either to calculate angles or to simplify trigonometric expressions. So that's the basic structure in this section. Well, let's begin with complementary angles. Complementary angles are angles that if you add them up, you will get 90 degrees or pi over 2. So let's write that down. Add up to, I'll just write it down in degrees and radians. So 90 degrees or pi over 2. So this is the key thing. If two angles add up to this, not that individually they're that, but if they add up to that, then they are complementary angles. Okay, so let's write this down. So we described it. Now we're going to write it down in symbolic form, but we're going to say the same thing that I've said in this sentence in symbolic form. So we say, in other words, theta and pi over 2 minus theta are complementary because of this relationship. We have, make this up, because theta plus pi over 2 minus theta, it's going to give us pi over 2, right? Theta plus pi over 2 minus theta, it's going to give us pi over 2, because these two pi and minus theta and minus theta cancel out. They add up to 0, and we get pi over 2. So this symbolic description matches the description we gave here. Okay, so theta and pi over 2 minus theta are complementary angles. So we had to mention this because the relationship between trigonometric relationship between complementary angles is very important. So we will look at that next. That's the second topic. Between complementary angles, like that. So to explore this relationship, we've been working with right triangles quite a bit so far, right? So let's consider the right triangle again. It's always useful in trigonometry. So consider the following right triangle. Right? So let's draw one. I'm going to draw it in this corner, like that. Then a line here. So this would be our 90-degree angle right here. And let's connect these two points or vertices like that. So we know that this angle is pi over 2. Remember that the sum of the angles within any triangle should be 180 degrees, right? So if I call this angle theta, let's call it theta, then if the summation of all angles within any triangle is 180 degrees, and I know this corner angle is pi over 2 or 90 degrees, so these two guys should add up to 90 degrees, right? Because this plus that is 90 degrees plus 90 degrees, we get 100 degrees. So if I know the measure of this angle is theta, then this angle should be pi over 2 minus theta, right? So if you add these plus this, we should get 180 degrees. Add these two, you get pi over 2, which is 90 degrees, plus another 90 degrees, you get 180 degrees. So the measure of this theta angle is theta. The measure of this angle is pi over 2 minus theta. So let's give these corners and sides some label. So let's call this corner B or vertex B. This one vertex A. This one vertex capital C. And we're going to give each side a length that is, and we're going to label it with a letter that is opposite to the labeling of the angle, opposite to it. So if this angle is A, capital A, we're going to say the length of this side is lowercase a. If the measure of this, this vertex is B, then the length of this side opposite to this corner is lowercase b, and the length of this side opposite that corner is C. Okay, so given this labeling, we should be okay now to discuss those relationships. Yeah. So in this triangle, given the discussion we just had about complementary angles, we know that theta and pi over 2 minus theta are complementary angles, right? So let's write that down. We know that theta and pi over 2 minus theta, these two angles, are complementary. They add up to 90 degrees. Complementary, okay? So let's explore the relationship between these complementary angles, theta and pi over 2 minus theta. So what I'm going to do is I'm going to, given this right triangle, I'm going to write down the basic trigonometric function for this theta angle and this pi over 2 minus theta. So we have the 6 basic trigonometric functions, right? Sine, cosine, tangent, cotangent, and secant and cosecant, right? So I'm going to write down using this right triangle, write down those 6 trigonometric functions for each of these angles. I'm going to do it for the theta, and then I'm going to do it for pi over 2 minus theta to see what relationship is there between the trigonometric relationships of these 2 complementary angles. So we need to list those first. So I'm going to do that on this side. I'm going to say that this side is the trigonometric functions for theta on this side. So, right, like that. And on that side, I'm going to write down the trigonometric functions for pi over 2 minus theta. I'm going to list the easier first, and then we're going to switch over to this one using this right triangle. So let's begin with the sine of theta first. So sine of theta, right, sine of this angle, is equal to the opposite side divided by the hypotenuse, right? So that'll be b over a. The opposite divided by a hypotenuse. So let's do the same thing for cosine of theta. The cosine of theta is equal to the adjacent side divided by the hypotenuse. So c over a. Then the tangent of theta is equal to, the tangent of theta is going to be equal to the opposite side divided by the adjacent side. So b over c. Then the cotangent of theta is equal to the adjacent divided by the opposite, or the reciprocal of the tangent of theta. Either way, you can get that from the right triangle, or you can get that from this tangent. As long as you know the tangent, you can flip those and you can get or you can obtain the cotangent. So c over b, then secant of theta, right? Secant is the reciprocal of which of these? Do you remember? Secant theta is the reciprocal of cosine theta. So it's a over c. And of course, cosecant of theta is the reciprocal of, do you remember which one? Cosecant of theta is the reciprocal of sine of theta. So a over b. A over b. Okay, so we're done with that. Now let's do the same thing for the complement of theta, which is pi over 2 minus theta. So I'm going to start from here and say that sine of pi over 2 minus theta, that would be the opposite side divided by the hypotenuse, right? Opposite divided by the hypotenuse. So that's c over a. Let's write down the cosine of that. Cosine of pi over 2 minus theta. Are you following what is happening? We're just doing the same thing, writing these 6 basic trigonometric functions for the complement of theta, which is pi over 2 minus theta. Okay, so cosine of pi over 2 minus theta would be adjacent side divided by the hypotenuse. So b over a. The tangent of pi over 2 minus theta, the tangent of this angle is equal to the opposite divided by the adjacent, right? Opposite divided by adjacent, which means C divided by B. Then cotangent of pi over 2 minus theta. Cotangent is just a flip or reciprocal of the tangent. So we can quickly write down B over C, right? Then the secant of pi over 2 minus theta. The secant is the reciprocal of, can you remember? Reciprocal of the cosine of that same angle. So it's the reciprocal of B over A, which would be A over B. And cosecant of pi over 2 minus theta is the reciprocal of sine of pi over 2 minus theta, right? So if sine is C over A, cosecant of that angle would be A over C, like that. Okay, so now compare the trigonometric values of these functions of theta with the trigonometric function values for the complement of theta. What do we have? Let's see. We have B over A. Do we have B over A? Right there. So B over A, B over A. What does that mean? It means cosine of pi over 2 minus theta is equal to sine of theta. So let's write that down. So we're going to compare these two sides and write down new formulas or relationships for trigonometric functions. So B over A, B over A. So that means cosine of pi over 2 minus theta is equal to sine of theta, like that. So that's a new relationship that we arrived at, right? So let's go to the next one. Cosine of theta is equal to C over A. Do we have C over? Oh, right there. C over A, C over A. So what can this tell us? It tells us that sine of pi over 2 minus theta is equal to cosine of theta. So let's write that down. Sine of pi over 2 minus theta, which is C over A, is equal to cosine of theta. Then tangent of theta is equal to B over C, right? Do we have B over C right there? So what does this mean? It means that cotangent of pi over 2 minus theta is equal to tangent of theta, right? They're both equal to B over C. So let's write that down. Cotangent of pi over 2 minus theta is equal to tangent of theta. And that's another new relationship or formula we have. Let's move down to the cotangent of theta. So we have cotangent of theta equals C over B. Do we have C over B right there? C over B, C over B. So that means tangent of pi over 2 minus theta is equal to cotangent of theta. So let's write that down. Tangent of pi over 2 minus theta, which is C over B, is equal to cotangent of theta. Let's box that like this. So next one is secant of theta equals A over C. Do we have A over C here? Right there. So what can this tell us? It says that cosecant of pi over 2 minus theta is the same thing as secant of theta, the complement angle, right? So cosecant of pi over 2 minus theta is equal to secant of theta. Almost done here. And then we have the cosecant of theta equals A over B. Let's look over here, right there. So cosecant of theta is equal to A over B. Secant of pi over 2 minus theta equals A over B. So this tells us that secant of pi over 2 minus theta is equal to cosecant of theta, like that. Okay, so these are the relationships between trigonometric functions of some angle and the complement of that angle, the angle that if you add to the theta will make it equal to 90 degrees. Okay, so let's see, now that we have this, let's put it to the test. Let's see if this is actually true. So I'm going to use my calculator for that. So examples. So let's see, let's take any angle. So for theta equals 150 degrees, right? When you do this, make sure that your calculator is in degree mode. If you wrote something in radians, please make sure that your calculator is in radians mode. Otherwise you get error. You get values that are not correct. So I'm using degrees, and I want to show you here, if I click this, see the degree here is underlined. So it means that my calculator setting currently is to degrees. It's set to degrees, okay? And I'm using degrees. So I'm fine here. So I'm going to get rid of that. Okay, so let's test this with this angle, with any of these. I mean, we can test it with this one, with sine of pi over 2 minus theta equals cosine of theta. So if that's true, then this would be sine of 90 degrees minus 150 should be equal to cosine of 150 degrees, right? So let's see. So we have on the left-hand side, so this is the left-hand side. We're going to use this. We're going to test that one. Let me write that down. Using sine of pi over 2 minus theta equals cosine of theta, right? Using that. So what is the left-hand side equal to? Let's say LHS, or left-hand side here, would be equal to sine of, because this is degree, I'm going to use the degrees version of pi over 2, which is 90 degrees minus 150 degrees, right? What is that equal to? So that would be 90 minus 150, that would be minus 60 degrees, right? So let's find out the sine of minus 60 degrees. So sine of minus 60 degrees equals, we got minus 0.866. I'm going to just stop at that point, but you can, but it's 0.25 and so on. If you want, we can write that down too. So that is equal to minus 0.866025. Okay, so now the right-hand side, which is cosine of theta, would be equal to cosine of theta, right? Or cosine of 150 degrees. So according to this formulas, these two should be equal to each other. Let's see if they are. So I'm going to put this here, and cosine of 150 degrees, and enter, minus 0.866025. So they are equal. So we're just verifying that the formulas that we just came up with. We're just verifying that they are in fact working properly. So yeah, they're equal to each other. Okay, let's do another example. Let's do this time, let's do with one of the cotangent tangent ones, right? With these two. So let me pick that, or maybe pick that one, tangent of pi over 2 minus 3. It makes no difference. So I'm going to pick this one. So suppose, so another example. So for theta, let's pick another theta, say 220 degrees, right? Using that one that I just pointed to, tangent of pi over 2 minus theta equals cotangent of theta. We want to test to see if this formula works. So the left-hand side, and I want to also highlight, this is the left-hand side, this is the right-hand side, right? And we did that here. This time, this is the left-hand side, this is the right-hand side. Okay, so first we're going to look at the value of what we have on the left-hand side. Let's do that. Left-hand side is equal to, we're testing this, so tangent of 90 degrees minus 220 degrees, right? Like that. So 90 minus 220, it's minus 130 degrees, right? So let's calculate tangent of minus 130 degrees. Maybe I should. I want to put this where you can see both that expression and the calculator. I think this should be okay. So tangent of 90 minus 220 is minus 130, close parentheses, enter. What do we get? We get 1.19175. I'm going to write down these numbers all the way till 5. So 1.1, my inks are drying, so let me grab another one here. So 1.19175. Okay, so that's what the left-hand side is. Let's look at the measure of the right-hand side. So RHS, or right-hand side, is equal to cotangent of 220 degrees. So let's evaluate that. So cotangent is simply, so cotangent of 220 degrees. Okay, so because, notice, I'm glad we got to this point. See, on my calculator, there is a tangent button, but there is no cotangent button, right? There is inverse sine, inverse cosine on top of this, inverse tangent on top of this, but there's no cotangent. Why do you think that is? A lot of scientific calculators don't have that key. You might find one that has one. I don't know that, but many, many, many ones, as far as I've owned, they have no key for cotangent. Why? Well, because you don't need them. Because cotangent is the reciprocal of the tangent. So if you know the tangent, you simply take the reciprocal of it, or you say 1 divided by that, and you get the value for cotangent. So they're saving space on the keypad here by omitting that one. You don't really need it. Okay, so let's write that, let's reflect that here. This is equal to 1 over tangent of 220 degrees. So if I find tangent 220, I take the reciprocal of it, or 1 divided by it, and I'm going to be able to get cotangent 220. So let's find out what that is. 1 divided, I'm going to calculate tangent of 220. Like that. So tangent of 220 equals that number. So let's write it down. 0.8390. I'm going to write down all the way to 6. 390,996. Like that. Okay. So let's take the reciprocal of that. The button on my calculator that does that is this x2 negative 1 power. So I'm going to do that. And there it is. So let's write that down. 1.19175. Compare that number with this number. Are they the same? Yes. And we knew that because we derived that equations based on the right triangle between relationships of angles between any angle and its complement angle. Again, complementary angles are angles that add up to 90 degrees. Okay, so after this, we can move forward. This is true with cosecant and secant. Just remember that if, for example, you have cosecant, if you want to test out more angles, you can go ahead, at home I mean, and do that. Just remember, for cosecant and secant, you're not going to have any keys here, right? Again, the calculator, those who manufactured this calculator were aware of the relationship between trigonometric functions, so they wanted to save space on this keypad, and they did a good job, I think. So there is no cosecant or secant button on this. Why do you think that is? Well, you know that the cosecant function is the reciprocal of the sine function. So if you are interested in calculating the cosecant of any angle, you simply calculate the sine of it with this button, and then you take the reciprocal of it with this button, and you have the measure of the cosecant angle. By the same token, there is no secant button on this calculator. So if you're interested in calculating the secant of any angle, you simply find the cosine of that angle, because the secant function is the reciprocal of the cosine function. So you find the cosine function, you take the reciprocal of it with this button, and you have the measure of that function, the secant function for that angle. Okay, so now we can move forward to the squared identities. So squared identities So you've seen this before. I'm going to write them down again. Very, very useful, extensively used in all of trigonometry, all the way through Calculus 3 for those of you who will be taking that course. So sine squared theta plus cosine squared theta is equal to 1. Very neat formula, right? If you have the squared of sine squared and cosine squared of some angle, they add up to 1. It's very neat. And tangent squared theta plus 1 is equal to secant squared theta, like that. And of course, the cotangent squared theta plus 1 equals cosecant squared theta. So these are the squared identities. So we're going to use these to simplify trigonometric functions. I mean, not exclusively these, but the other functions that we know of as well, right? So we do know, I mean, I probably it's a good idea if I write them down just as a reminder. So we know that sine and cosine are pretty straightforward, but the tangent of theta, remember that? Tangent of theta is equal to sine of theta over cosine of theta. So that's a very important formula. The other formula that we have that is very useful is cotangent of theta is the reciprocal of the tangent of theta, right? So it's cosine of theta divided by sine of theta. Also, we know that the secant of theta is equal to reciprocal of cosine of theta, right? Remember that? And of course, the cosecant of theta is equal to the reciprocal of the sine of theta. So these are very helpful in simplifying expressions, but of course these are also helpful, but we've been using these a lot, but not much so these ones. So we're going to use these to simplify trigonometric expressions. That would be item number 4. So using the above identities to simplify trigonometric expressions. Okay, let's jump right into some examples. That's the best way to do this. So we want to simplify this expression. Let's start with an easy one. Simplify cosine of t times cosecant of t. Okay, so we want to, we want to simplify this. Okay, so we can do that. Cosine of t is cosine of t. It doesn't get any more basic than sine and cosine, right? But when we get to tangent and cotangent, then those next functions like that can be connected to the sine and cosine. But cosine and sine are the most basic trigonometric functions. So I'm going to write this down. I can't reduce this to anything less than what it is. So cosine of t times, I can do something with this, right? Cosecant of t function, which trigonometric function is this connected to? Do you remember? It's the reciprocal of which one? Sine of t, exactly. So this times reciprocal of, so instead of that, I'm going to substitute with that with sine of t, right? Instead of cosecant of t. So what do we get? We get cosine of t divided by sine of t after you multiply, right? Cosine of t times 1 is cosine of t over sine of t times 1, which is the denominator. I'm not going to write it down, but cosine of t has a denominator 1. 1 times that is sine of t. And that is equal to, simplifying this, we get cosine divided by sine. What trigonometric function does that represent? Do you remember? Cosine divided by sine is cotangent of t. So cotangent of t, like that. Okay, so we want to simplify We want to simplify this expression. Cosine squared theta times 1 plus tangent squared theta, right? So we want to know how we can simplify this. Again, first I'm going to begin with the 1 plus tangent squared theta, because cosine and sine usually are basic ones, basic trigonometric functions. So I won't mess with those unless I see a way out of, or I see a useful way of for doing that. Otherwise, if I have no reason, I don't really mess with cosine or sine of theta, because they are the very, very basic trigonometric functions. But this one, tangent, sure. Let's look at what we can do with what we have inside the parentheses. So I'm going to rewrite the cosine squared theta. So this is cosine squared theta times, now we have one of the squared identities that we have. Of course, so 1 plus tangent squared theta is the same thing as tangent squared theta plus 1, right? It makes no difference. And that is equal to secant squared theta. So let's substitute that. This is simplification because we went from 2 terms to 1. Secant squared theta, right? We went from 2 terms to 1, so that's our expression now. It's a little bit more simplified than what we had before. Now you know that secant of any function, or secant function, is the reciprocal of the cosecant function. So let's write that down. So cosine squared theta times 1 over cosine of theta squared, right? Secant squared theta is equal to 1 over cosine theta, which is secant of theta squared. So let's take this one more step. So I'm going to put this power on the inside. So cosecant squared theta times 1 over cosine squared theta. You see where it's going, right? Now multiply cosine squared theta times 1. We have cosine squared theta divided by, the denominator is 1. 1 times cosine squared theta is cosine squared theta, right? And what is that equal to? 1. So this is really the power of simplification, because this is really 1. So why keep it like that when we can replace all of that with number 1? Okay, so that's the power of simplifying expressions. Let's do more example. We want to simplify. By the way, guys, I mean, I don't know if you're doing this at home, but if you're not, I highly encourage you to grab a pile of scratch papers and pause the video, give it your own thought, give it the best shot, try to remember these trigonometric functions we're using, try to remember them, memorize them, and try to see the relationship between them and solve these. Then come back to the video and see what I've done. If you do that, you will build a very strong foundation of all of this moving forward. And hopefully exams will be very easier, much easier for you that way. Okay, so we want to simplify this expression. Secant of x minus cosecant of x divided by tangent of x, right? We want to simplify this. Okay, so we remember these, what other trigonometric functions these are connected to, right? So like I was saying a minute earlier, the cosine of any angle or sine of any angle, Those are very, very basic components of trigonometric functions. So usually we can't really go simpler than that. But secant, cosecant, tangent, cotangent can be broken up into relationships with sine and cosine, which we can then cancel out or simplify. So let's tackle the secant of x and tangent of x, but we're going to leave the cosine of x alone. Okay, so secant function is the reciprocal of, do you remember which one? Reciprocal of cosine function, right? So let's write that down. So we have 1 over cosine of x, or this can be x or theta or u or t. It makes no difference. We've been using theta, so why not use x now? So this is that. Minus, I'm going to leave cosine of x alone, so cosine of x divided by tangent of x. Remember what connection this has with sine and cosine? Tangent of x is equal to sine of x divided by cosine of x. If you said that, wonderful. So sine of x over cosine of x. Then in the denominator we're fine, but we have here two terms that we can combine, right, using the common denominator. So the common denominator would be which one? If the denominator here is 1, the common denominator would be cosine of x. So let's do that. So this is just simplifying from that. Simplifying from that to here. So we have let me use another color so they don't get mixed up because I'm really too close to those terms. So we have cosine of x. Now this expression, this term, already has the common denominator, right? So if I do, because I want to make sure that you guys follow this. So we're taking the common denominator, I'll do it in this corner, 1 over cosine of x minus cosine of x over 1, right? The denominator here is 1. So we know the common denominator is cosine of x. Now, this one is fine, right? It doesn't need anything to be multiplied by it. So I'm going to write down 1. Now, minus is minus. But this denominator is not cosine of x. So what does it need? It needs a cosine of x to be multiplied by it. And if we're doing this to the denominator, we have to do this. We have to multiply the numerator by cosine of x, right? So cosine of x over cosine of x multiplied by this, we get 1 minus cosine squared x. Sorry, I'm running out of room there. I should have seen it. So this is just showing you what is happening here as we take the common denominator. So the numerator here will be 1 minus cosine squared x. And the denominator, of course, stays the same. So sine of x over cosine of x. Okay. So now we can have a complex fraction, right? So we need to simplify this. So the quick trick, there are other ways of simplifying a complex fraction, of course, but they're a little bit more time consuming than what I'm going to show you. Whenever you have complex fractions, the easiest way to simplify them is take the farthest terms away from each other. That would be that and the 1. The terms that are farthest away from each other, and multiply those by each other. So cosine of x times 1 minus cosine squared x divided by the product of the nearest terms. These two terms are nearest by each other. So multiply them and put them in the denominator. So we have cosine of x times sine of x. If you're wondering why am I putting parentheses around x here, not there, it's just the parentheses is not necessary, but it's a visual aid because I have letters here, S, I, N, and an X. By putting parentheses around it, I'm making sure that visually you are able to distinguish the argument of this function with the rest of it, with the operator. So the sine is the operator and x is the argument. That's all. If you don't put the parentheses, it's no big deal at all. It's a visual aid. Okay, so now we can simplify this a little more, right? Let's see. Yeah, we can still do it. I should have done something here, but it's no big deal. We can still simplify that. So cosine of x and cosine of x cancel out, and then I should have done earlier, so equals 1 minus cosine squared of x divided by sine of x. But from using the squared identities, right? So using the squared identity that sine squared of x plus cosine squared of x equals 1, using that, let's algebraically move things around. So sine squared of x is equal to 1 minus cosine squared x, right? I just moved cosine squared x to the other side. So we can substitute in the above expression for 1 minus cosine squared with sine squared x, right? Okay, so let's do that. Equals sine squared, instead of that, sine squared x divided by sine of x, right? So, but sine squared of x is sine of x times sine of x, right? That's what sine squared of x is. So divided by sine of x. Now we can cancel one of these. So we end up with sine of x over 1, which is sine of x. That's the final result. So compare this expression with this expression. So this is really sine of x. This is the power of simplification. That's why we have so many ways, different ways of simplifying expressions, because why keep this when we know that expression is equal to this, right? Much more compact and easier to work with. Okay, let's do another example. So we want to simplify sine of x. If you want, I can put a parenthesis around that. Too many letters, right? S, I, N, and x. It helps if we put a parenthesis around the argument. Over cosecant of x plus cosine of x divided by secant of x. And we want to simplify this expression. Okay, so as I mentioned before, the sine and cosine functions are the most basic trig functions, so I'm not going to mess with those. But I am going to do something about cosecant and secant, because we can break these two up into their components of sine or cosine, whichever one is relevant. Okay, so let's do that. So we know that the, let me write this down. So sine of x divided by, we know that the cosecant function is the reciprocal of which function? If you said sine function, you're absolutely correct. So let me replace cosecant of x with its reciprocal of the sine of x. So 1 over sine of x function, right? Plus cosecant function, or cosine function, not cosecant, cosine function divided by, now secant function is the reciprocal of which function? Do you remember? Reciprocal of cosine function. So 1 over cosine function, cosine of x function. Okay, so now what we did, we got rid of cosecant and secant. But guess what happened? We now have complex fractions. We can't have that, right? We need to simplify this complex fraction. So now, what I showed you here, that whenever you're simplifying a complex fraction, multiply the farthest terms from each other. The farthest terms, multiply them and write it in the numerator. Divide that by the product of the terms that are the nearest of each other, closest to each other. Divide by cosine of x times sine of x. That's the quickest way to simplify. So we know that the denominator of sine of x is 1. The denominator of cosine of x is 1. So now, let's do what I just suggested a couple of seconds ago in order to simplify this complex fraction. So the farthest terms from each other are sine of x and sine of x, right? Multiply them. Sine of x times sine of x divided by, multiply the nearest terms, 1 and 1. 1 times 1. So we're done with this one. Let's do the same thing to simplify this. So go ahead, if you haven't done this already, pause the video, run through this, and then come back to the video to see how your solution matches mine. I hope you're doing that. That way you will build a very strong trigonometric background moving forward. So I'm hoping that you've done that. You're back, and now let's continue with this. The farthest terms here are cosine of x and cosine of x. So we're going to multiply them by each other. Divide that by the nearest terms, 1 times 1. Okay. So sine of x times sine of x, it's sine squared x plus, that's over 1, right? So I can write it as sine squared x plus cosine x times cosine x is cosine squared x over 1 is the same thing. So how do we simplify this? Do you remember the squared identities? Do you remember? Let me bring them back. So compare that, what we have, with the squared identities. Which one can we use? The first one, right? Sine squared theta plus cosine squared theta equals 1. So we can say sine squared x plus cosine squared x equals 1 as well. And we are done with that one. So now, we're going to do the same thing, but in a different way. So far, notice that we were simplifying, right? So there was no equation. It was just simplify. So there was no equation there. I put the equality to indicate that I'm simplifying it to this. But it was just an expression. Now, we're going to verify what we learned so far. We're going to use that to verify the both sides of an equation, to verify if an equation is true. So let's do that. So we want to in these expressions. So we want to verify that the following equations are true. Okay, so this is what I mean. So now we're going to have an equation. We have tangent of y divided by cosecant of y equals secant of y minus cosine of y. So we want to show if the left-hand side is equal to the what we have on the right-hand side. Right? That's the right-hand side right there. Okay, so to do that, let's begin with the expression on the left-hand side. Okay, so we have left-hand side is equal to tangent of y divided by cosecant of y. So this, we can break this up into sine of y. Remember that? Divided by what? Do you remember divided by what? Divided by cosine of y. Divided by cosecant is the inverse of sine function. If you said that, wonderful. So 1 divided by sine of y. Now, when I said what I said earlier is that whenever you have complex fractions like this, then simplify them very quickly like this. Take the farthest terms from each other. Sine of y, multiply them. What do you get? Sine of y times sine of y is sine squared y divided by the product of the nearest terms. Cosine of y times 1 is cosine of y, right? That's from the left-hand side. This is as far as we can take it. Now let's see what do we get by simplifying the right-hand side. So the right-hand side, or RHS, is equal to that. So secant of, well, let me bring this down. So secant of y minus cosine of y. Cosine we can't touch, right? It's very basic, like the sine function. It's a basic trigonometric function, but this we can. Secant function is equal to the reciprocal of some function, right? What function is this a reciprocal of? Do you remember? Secant function is the reciprocal of cosine function. So replace it with that. 1 over cosine of y minus cosine y. Now, we need to take the common denominator here. So let's do that. I guess I can fit that, the rest of this here, because I'm going to need the space. So let me try, and yeah, I can fit it here. So equals, the common denominator here is 1, right? Sorry, the common denominator here I meant is cosine of y. So this denominator is 1, which means the common denominator is cosine of y. So let me write that down, cosine of y. So do we have to multiply this fraction by anything? No, because the denominator of this fraction is already there. But do we have to do anything here? Yes. The denominator here is 1. We want it to be equal to the common denominator. So we're going to have to multiply this denominator by cosine of y. But we can't just multiply the denominator and not do the same thing to the numerator. So we're going to have to multiply the numerator by cosine of y as well. So we're multiplying the second in term by cosine of y over cosine of y, and there's a negative there. So what do we end up with? We end up with 1, because we didn't have to do anything to this, right? So the numerator stays the same, minus cosine of y times cosine of y is cosine squared y. Oops, I barely was able to fit it in that corner. Okay, so now, do you remember how we can, the denominator cannot be simplified, right? The cosine and sine are very basic, but what about this expression, 1 minus cosine squared y? Well, we just did it in the previous example. We made use of the squared identities. We said that 1 minus cosine squared x is equal to sine squared x, right? This is based on this identity, on this identity. If you algebraically move cosine squared theta to the other side, you'll get 1 minus this on the other side, which is equal to sine squared theta. That's what we did for this one. So we ended up with, instead of 1 minus cosine squared x, we ended up with sine squared x. So we're going to do the same thing here. Instead of 1 minus cosine squared y, we're going to end up with sine squared y over cosine of y. And this is the right-hand side. Right? So compare the, let me move this up a little bit. Okay. So compare the left-hand side. The left-hand side was that quantity, remember? Sine squared y over cosine y. We just worked with the right-hand side, and we ended up with this, sine squared y over cosine y. So we've shown that the left-hand side and the right-hand side are equal. So we verified the equation. So left-hand side is equal to right-hand side. We've just shown that. So we've verified the equation. Okay? I hope this is becoming clear as far as how we verify if the equations are true. So let's do another example. Suppose we want to now verify this equation. So let's call this B. So verify parentheses sine of x plus cosine of x squared equals 1 plus 2 sine of x cosine of x. I'm running out of room there almost. Cosine of x. Okay, like that. Okay, so the left-hand side is that. That's the left-hand side. This is the right-hand side. So if we want to verify this equation, we need to, so that's a question mark, right? We're verifying that the left-hand side is equal to the right-hand side. We need to show that. So the left-hand side, let's expand this. That's the binomial squared, right? We know exactly how to expand these. So sine squared x plus twice sine of x times cosine of x plus cosine of cosine squared x. Like that. Okay, so notice that the middle term, we will later on in this course, we will get to another formula which shows us how we can simplify this middle term. But for now, we're going to keep it like that. but keep that in mind, that we have a formula that will simplify this. But for now, let's keep it. But we do have the squared identities that tell us that sine squared x plus cosine squared x equals 1, right? So let's substitute. So we have equals, the left-hand side is equal to 1 plus 2 sine of x times cosine of x, right? Okay, so now let's look at the right-hand side. What can we do with that? Look at that. We're already done, right? Because the right-hand side is already what we have for the left-hand side. 1 plus 2 sine of x cosine of x. On the right, we have 1 plus 2 sine of x cosine of x. So we're already done. So left-hand side is equal to, or is, the 3 lines means exactly equal to, is exactly equal to the right-hand side. So we have verified the equation. Let's do another example. Suppose we want to verify this equation. We have cotangent of minus alpha. Alpha is another Greek letter that is often used in trigonometry as an argument of a trigonometric function. So alpha, beta, omega, all of the theta, or phi, all of these are Greek letters. Phi, sorry, not theta, but phi, theta, and so on. So then cosine of minus alpha plus sine of minus alpha equals minus cosecant of alpha. So we want to show that this equality is true, right? That is true. So the left-hand side, this is our left-hand side. This is our right-hand side. So let's see the right-hand side. It can be simplified. It can. We can simply rewrite this very quickly, right? As minus the reciprocal of which function? Sine function, minus 1 over sine of alpha. We can quickly do that. So this left-hand side is more demanding, so let's simplify this. So we have left-hand side equals the cotangent of negative alpha can be written as a ratio of which two trigonometric functions? Do you remember? The cotangent can be written as cosine divided by sine. So let's do that. Cosine of negative alpha divided by sine of negative alpha. This is where our discussion of even odd trigonometric functions becomes very, very useful, because which two trigonometric functions are even? Do you remember? Out of this 6, sine, cosine, tangent, cotangent, cosecant, secant, out of these 6 trigonometric functions, which ones are even? There are only 2 of them that are even. Do you remember which ones? They are cosine and reciprocal of cosine, which is secant function. Only those 2 functions are even. The other 4 are odd. So that means cosine of negative alpha is equal to cosine of alpha. And that itself simplifies the numerator here. And sine, because it's an odd trigonometric function, sine of negative alpha will be minus sine of alpha. Okay, but we'll get to that. So for now, we're going to multiply that by, so we have cosine of negative alpha. We can even now we can probably write that as, well, let's for now, let's keep that. So times cosine of negative alpha, even though I could write it as cosine of alpha, it's okay for now. Let's keep it. And then plus sine of alpha. Plus, plus sine of negative alpha. Okay. So now recall that. That cosine of negative alpha is equal to cosine of alpha. This is because cosine is even. It's even. And I want to highlight this so that. And sine of negative alpha is equal to minus sine of alpha because sine is odd function. Okay, so knowing that, let's substitute these with their equivalent even odd forms. So we have the left-hand side we're still simplifying the left-hand side, right? The left-hand side will be cosine of alpha divided by minus sine of alpha. Do you see the transition from this to this? Times cosine of alpha minus sine of alpha. Okay. All right. So let's simplify this more. We have in the left-hand side, we have cosine times cosine. We have cosine squared alpha over minus sine of alpha. Right? I'm just distributed this to this. Minus sine of alpha. Okay. Okay, so now what would you suggest that we do at this point? What would you do? Well, you would take the common denominator, right? This is a subtraction. Addition or subtraction of two terms. We would take the common denominator. So let's do that. So the left-hand side is equal to, what would be the common denominator? The common denominator would be minus sine of alpha. So the denominator here is 1. So the common denominator, we have minus sine of alpha. Do we have to do anything to this fraction? No, because the denominator is already equal to the common denominator. So I'm going to write down cosine squared alpha. Then the minus. Do we have to do anything to this fraction? Yes, because the denominator is 1, not minus sine of alpha. So let's multiply both the numerator and the denominator by the minus sine of alpha to make the denominator what we want, right? So times minus sine of alpha divided by minus sine of alpha, like that. So our goal is to get this one to be minus sine of alpha, but which means we have to multiply the denominator by that, minus sine of alpha, but we can't ignore multiplying the numerator by that as well. Okay, and the ratio of this over that is just 1. So we're multiplying this by 1, by a ratio of 1, which doesn't change anything here, but it gives us the common denominator that we want. Okay, so Now we have the common denominator here. What happens in the numerator? Well, this minus and this minus multiply together. What will happen? It'll be positive, right? It goes from minus to positive because we're multiplying it by that. And then, of course, the sine squared alpha. Okay, so how do you simplify this then? Can you simplify that? Do you see how easily we can simplify this? Cosine squared alpha plus sine squared alpha. What is that equal to? Do you remember the squared identities? Remember this? Sine squared theta plus cosine squared theta is equal to 1, right? So this numerator is equal to 1 divided by minus sine of alpha. Okay? Or you can write this as minus 1 over sine of alpha. This minus can be up here in front or down in the denominator. So this is what left-hand side is. That's the left-hand side right there. So what about the right-hand side? So let's write that down. Right-hand side, it was equal to minus cosecant alpha. Well, cosecant alpha can be written in terms of the reciprocal of which function? Sine of alpha, right? So minus 1 over sine of alpha. And this is the right-hand side, right? That's the left-hand side. This is the right-hand side. Compare them. So left-hand side is equal to right-hand side, and we have been able to verify the equation, the original equation. Okay, so that's that. Let's do another example. Please pause the video as we're moving. The first, maybe not the first one, even though you can do that in the first example too, but now we are several examples along, so you've seen quite a bit of what we can do with these identities. And so please pause the video in this next example and complete the solution on your own, and then come back to the video. So here we would like to verify so we want to verify this equation. We have sine of x plus cosine of x to fourth power equals 1 plus 2 sine of x cosine of x squared. Okay. All right. So both sides are even powers, have even powers, right? So let's take the square root of both sides. So taking the square root of both sides, we're going to have plus or minus on both sides, right? So they cancel. Because the even power, we're going to have plus or minus on this side, plus or minus on that side, and the plus or minus cancels out. It just, we're back to this side equal to that side. So that'll be, so take the square root of sine of x plus cosine of x to the fourth power equals square root of 1 plus 2 sine of x cosine of x squared, right? Just taking the square root of both sides. And what do we end up with? We end up with sine of x plus cosine of x squared, right? this 4, and the index of this square root, which is 2, it's 4 over 2, going back to the properties of radicals, right? This 4 divided by 2, any radical can be written in terms of rational exponents. So if I wrote this, I would get 4 divided by 2 without the radical, and 4 divided by 2, 2 being the index of this, we get 2, equals, so that's from basic Math 124 or even Math 96 courses. On this side, it's just 1 plus 2 sine of x cosine of x. Like that, okay? Because this 2 and this 2 index, 2 over 2 is 1, and they cancel each other out. Okay, so now the left-hand side, let's see what the left-hand side is. So this is the left-hand side. This is the right-hand side. Let's expand this because this is binomial squared. So we have sine squared x plus 2 sine of x cosine of x plus cosine squared x equals 1 plus 2 sine of x cosine of x. Okay, so the middle term, we will learn how to simplify 2 sine of x cosine of x. Well, it's this expression in the middle, we haven't gotten to it, but I'll mention it anyway. It's equal to sine 2x. So sine 2x, it's equal to 2 sine x cosine x, but never mind that for now. I'm just giving you a heads up that this can also be simplified, but we're not going to do it because we haven't gotten to that section where we can talk about that formula. For now, we can only simplify these two, sine squared x plus cosine squared x. That will simplify, right? Let me bring back the squared identities. Sine squared x plus cosine squared x. Sine squared theta plus cosine squared theta equals 1. Let's not forget about these. We haven't used these two squared identities much, but they are very, very important, and they will become handy in the future. So tangent squared theta plus 1 equals secant squared theta. Cotangent squared theta plus 1 equals cosecant squared theta. Okay, so in here, we're going to have, here's the left-hand side and the right-hand side. And then I'm going to simplify the left-hand side. It's going to be 1, this sine squared x plus cosine squared x, 1, plus the middle term, which is 2 sine of x times cosine of x. So that's the left. Look at the right-hand side, right? It's already there. So we've already shown that the two sides are equal. Therefore, we have verified that the equation is true. So from these two, we have the left-hand side equals the right-hand side, and we're done with that. Let's do, and I hope you, like I was saying earlier, I hope what you did was pause the video and then after you looked at my solution up to this point, after you had written down your own solution. Okay, so let's do another example. So this would be part E. We want to verify So let me write this down, so I don't think I have enough space there. But we want to verify this equation. Secant of theta times cosecant of, secant of t times cosecant of t times tangent t plus cotangent t equals secant squared t plus cosecant squared t. Okay, like I was saying, these parentheses are optional. I'm just using them to give it a visual clarity that those are the t is the argument here, or the variable. Okay, so the left-hand side, we will take the same approach. So this is the left-hand side, and this is the right-hand side, right? So let's start with the left-hand side, which is equal to all of that, secant of t times cosecant of t times tangent t plus cotangent t. Well, that is, the secant is the reciprocal of cosine t, so I'm going to rewrite that, 1 over cosine t times cosecant t. Cosecant t is the reciprocal of which function? Sine of t. If you said that, wonderful. And I'm hoping you've already done this on your own, and you're back to the video after you have your solution, like that, times tangent t. Now, tangent t is equal to sine of t over cosine of t, right? So let's break it down to its most basic trigonometric function components, like that. And what about cotangent? Do you remember what cotangent was? It was the reciprocal of the tangent. So if you remember the tangent, you remember the cotangent. It's just cosine t over sine t. Like that. So now the left-hand side is equal to, let's multiply these or simplify them, and then we'll take the common denominator here, right? So 1 over sine of t times cosine of t, right, times, take the common denominator. What is that? That would be sine t times cosine t, right? Sine t times cosine of t. So multiply the numerator of each of these fractions by what's missing from their denominator when you compare it to the common denominator. So this common denominator, compare that to that. What's missing from here? It's sine of t, right? Sine of t is missing when you compare these two. Sine of t is missing, so multiply the numerator by what's the term that is missing. Sine of t times sine of t is equal to sine squared t, plus is plus. Now this denominator, right? Compare this denominator with the common denominator we have. What is missing from here? Cosine of t is missing, right? From here, when you compare this with this. Cosine of t is missing, so multiply the numerator of this fraction by the term that is missing. So cosine t times cosine t is cosine squared t, like that. Okay. So now the numerator, I'm sure you can see sine squared t plus cosine squared t, that is equal to 1, right? When we compare that with the squared identity. This keeps coming up, right? Very, very useful. But let's not forget about the other two squared identities as well. Okay. So let's simplify left-hand side a little more. So we're still going to have 1 over sine of t cosine of t times 1 over sine of t times cosine of t. So that. Okay, so now 1 times 1 is 1. Sine t cosine t times sine t cosine t is sine squared t times cosine squared t, right? So let's write that down. We have 1 over sine squared t times cosine squared t. So that's our left-hand side. So let's look at the right-hand side. So the right-hand side, so far we have that, right, for left-hand side. So the right-hand side was, you don't see it, it's off the screen, but I'm going to write it down here, was equal to secant squared t plus cosecant squared t, right? So let's break each of these down into their most basic trigonometric functions. So we have secant was the reciprocal of the cosine function. So square that. Instead of this, we get 1 over cosine squared t, right? I hope this didn't, going from here to here, didn't confuse anybody. So secant, the regular secant function is the reciprocal of the cosine function. This is a squared, so I squared 1 over cosine t, and I got 1 over cosine squared t, plus the cosecant function is the reciprocal of the sine function. So if this is squared, squaring 1 over sine t, it will be 1 over sine squared t, right? So 1 over sine squared t. So let's take the common denominator here for the right-hand side. Common denominator would be sine squared t times cosine squared t. So compare each of these denominators with the common denominator, right? We have the two fractions we're trying to combine. Comparing this with this, what's missing from this denominator? Sine squared t, right? So multiply the numerator by the missing term. So we have sine squared t times 1, it's sine squared t, plus, compare this denominator with the common denominator. What's missing from it? The cosine squared t, right? So multiply the numerator 1 by the cosine squared t. So cosine squared t. Okay, so now we have the, I'm sure you're picking up very quickly now what happens to the numerator, right? Sine squared t plus cosine squared t is equal to 1. So we have right-hand side is equal to 1 over sine squared t times cosine squared t. Okay, so now we have simplified this as far, the right-hand side, as far as it can go. Compare, if you would, the left-hand side with the right-hand side. Compare them. They're equal, right? So from this and from this, the left-hand side is equal to the right-hand side. So we have verified that the equation is true. Okay. Let's do another example. Just reminder, please pause the video after I write down the next problem. Please pause the video, write down your own solution, and then come back and compare that with my solution. So that's just the way, the nature of this subject. That's how we all study that. Okay, so we want to, that was part E. So this is part F. We want to verify this equation. We have sine of alpha minus tangent of alpha times cosine of alpha minus cotangent of alpha, and that's equal to cosine of alpha minus 1 times sine of alpha minus 1. Okay, so it barely fit across the page. Yeah, I'm glad that I should have started maybe a little bit this way. All right, so let's begin with the left-hand side, right? This is the left-hand side, and this is the right-hand side. And what we're trying to do is establish whether this equality is true. So we want to simplify this side, compare it with that side. Okay, so the left-hand side is equal to, let's expand this right away. So sine of alpha times cos, this is just a FOIL, right? We can FOIL this. Sine alpha minus tangent alpha times cosine alpha minus cotangent alpha. We can FOIL this. Sine of alpha times cosine alpha. And then, so this is what we're going to do. This multiplied by that, then this multiplied by these two. So let's do that. Sine of alpha times cosine of alpha. Then minus sine of alpha times cotangent of alpha. Then minus, right, minus cosine of alpha times tangent alpha. So minus that minus is coming from here, minus cosine alpha times tangent alpha, and then plus, right, plus minus times minus is plus tangent alpha times cotangent alpha. So plus tangent alpha times cotangent alpha. Okay, so left-hand side. So let's see what we can or cannot simplify here. The sine and cosine, they are the most basic components, so let's write them down quickly. And so this one, we have minus sine of alpha. Cotangent can be written in terms of cosine and sine, right? Do you remember how the ratio works? Cotangent of alpha is equal to cosine divided by sine. So cosine of alpha divided by sine of alpha. I hope I can fit this across the page. Minus cosine alpha, I'm going to write this down. I'll try my best. Times tangent alpha is the reciprocal of the cotangent alpha, right? So tangent alpha is sine alpha over cosine alpha. Like that. One more term here. Let me see if I can fit it. So times tangent alpha is sine alpha over cosine alpha. times cotangent alpha, which is the reciprocal of this. So cosine alpha over sine alpha. Okay, so let's see what we can simplify. Certainly, sine of alpha times this, these two cancel each other out. Over here, cosine alpha times this, they cancel each other out. And sine, when you multiply, that sine with this sine cancel out, and that cosine of alpha cancels out with that. So for the last term, we get plus 1. So, okay, so let's go through this. Left-hand side is equal to sine of alpha times cosine of alpha minus cosine of alpha, which is that, after simplifying, and then minus sine alpha, right, because the cosine alphas cancel out, minus sine of alpha plus 1. Okay, so we have the, that's the left-hand side. We have that here so far. That's what we have as far as we can take it for left-hand side, right? So let's see what we can do with the right-hand side. I'm going to write that down. Right-hand side is equal to, and this one, so we have cosine of alpha. It's off the screen there, but I'm rewriting it here. That times sine of alpha minus 1. Okay, you can see that's the same expression here, right? Okay, so now let's FOIL this, just like before. So that's the only thing we can do, right, at this point. So we have cosine alpha times sine alpha. It's sine of alpha times cosine of alpha. If you write cosine alpha times sine alpha, it's no different than this. I just prefer to write it this way, sine first and then cosine. And then minus cosine of alpha, right? Minus this times that. So we're foiling this times this, then this times that, and then minus 1 times that, minus 1 times that. That's what we're doing. And then minus cosine of alpha. So we're done with this. Then minus 1 times sine alpha is minus sine of alpha minus 1 times minus 1 plus 1. Right? That's after foiling that. So let's see what do we have. Well, we're done, right? If you compare this. So let's compare all of this for right-hand side with that. Compare these two equations. This is the left-hand side. This is the right-hand side. Compare them. They're identical, right? Like I was saying earlier, guys, if you had cosine alpha times sine alpha in any one of these, that still be identical, the same term. If you had cosine alpha times sine alpha minus sine alpha minus cosine alpha plus 1, it's the same thing. So if you had this over here and this over there, it makes no difference. These are identical terms between the left and the right-hand side. So we've proved that the equation is true. So left-hand side is equal the right-hand side. So we've proved our what we were asked to show. Okay. So let's do one more problem. So the nature of this example is different, but it's very interesting. It makes use of one of those squared identities that we haven't yet made use of, and that's nice because so far we've just used sine squared of x plus cosine squared of x equals 1. So this will have us use one of the other ones. So here we want to make substitution and simplify in here. So this is the problem we have. Square root of 1 plus x squared, and x is set equal to tangent of theta, right? Well, these are the given parameters to us. So we're asked to make the substitution and simplify. Let's do that. So we have, and I'll just use the blue ink here. So this is equal to square root of 1 plus, instead of x, I'm going to substitute tangent theta and square it. So tangent, let me put a bracket here, tangent theta squared. All I did was substitute for x with tangent theta, and I kept this squared. So this is equal to square root of 1 plus tangent squared theta, right? And then by squared identities, what do we have? We have 1 plus tangent squared theta, or tangent squared plus 1, right? So compare that with what we have here. It's the same thing, right? Tangent squared theta, 1 plus tangent squared theta is the same thing as tangent squared theta plus 1. What is it equal to? Secant squared theta. So let's substitute secant squared theta. So like that. That's theta, like that. And then what is that equal to? Take the square root of secant squared theta. It's just secant of theta. And you can either, I guess, what they like in trigonometry, I mean, this is fine, but I'm worrying about WebAssign. And when you work out one of these problems in WebAssign, what do they expect you to have as the final answer? If they accept that, I mean, on an exam paper, this would, I guess, it would do. It shows that you clearly understand how to simplify this expression and the connection between 1 plus tangent squared theta and secant squared theta, which is one of the squared identities. But I wonder how would WebAssign accept your answer. So I guess let me take this one step further. So after this, we want to simplify this to its cosine of theta equivalent, right? Secant theta is the reciprocal of the cosine theta or cosine function. So let's take this answer one step further and say that is equal to 1 over cosine theta. So when they say make substitution and simplify, I guess this would be the most simplified form of this whole expression. Okay? So you don't want to leave it like this, is what I'm saying. Take it all the way to the basic sine or cosine, whichever one applies. If we had cosecant of theta, we would write this as 1 over sine theta. In this case, secant theta is equal to 1 over cosine theta. Okay, so we've gone over, we finished section 1.1 in this video, and I thank you for tagging along as we go through each section, and I applaud you for that. And so when we come back next time, we will look at section 7.2. Until next time, have a nice day and see you later.